if you had to pick one topic that's bound to come up in the Astro paper, HR diagrams. Please get to know your HR diagrams. So let's explore them. Let's get our heads around the axes first of all. So first of all, the x-axis is temperature. Confusingly, it increases to the left. Please familiarize yourself with that. Don't get caught out by that. This is the surface temperature of stars. So we can catalogue all the stars we see according to surface temperature, which we'll do by Wien's law, which I'll make a different video about. So depends which one you look at. There is quite a lot of variation here, but we put the surface temperature here in Kelvin, about 30,000, down to say 3,000 here. So let's mark 10,000 there. Let's say go 6,000 here. So we can catalogue all our stars by surface temperature. For historical reasons, they're also classified by spectral class. So the very hottest we have are O-class stars. That's spectral class, which is just another way of classifying temperature. So O and B and A is about here, and F and G and K, and down here the coldest is an M. O, B, A, F, G, K, M. For historical reasons, you might remember the mnemonic, O be a fine girl or guy, kiss me. So O being the hottest, M being the coldest. You might know that ours is surface temperature about 5,800-ish Kelvin. So we are a G2V star, or G25 rather, G25 star. So the G tells us our spectral class, reasonably standard. 2 isn't on our syllabus, we don't need to know that, but it just tells us how far along they are. So a G1 will be slightly hotter than us, for example. We can also classify all stars by their luminosity. And that's what the y-axis here is, luminosity. Normally done in terms of the luminosity of the sun. Circle on the dot means the sun, of course. So 1 is here. So the sun, our sun, is around about here on my diagram. Then it's logarithmic, so 100 might be here. 10 to the 4, 10 to the 6. So something here is 10,000 times as hot as our sun. So 0.01, 10 to the minus 4 here. So two quite confusing axes there, strange scales. So if we were to catalogue all the stars, Hertzsprung, N-E-R, Hertzsprung I think, and Henry Russell spotted a pattern. Let's see if we can see that pattern now. They seem to form, most of them, this pattern. So this diagonal line, with a bit of a curve to it around here. Top left to bottom right, of course that's because the temperature is this way around. So roughly along sort of here-ish, curving up at the end there. Quite a few around here. Quite a few forming a line along here. And then a few up here as well. So let's try and understand what these are, and then we'll look at some uses of the HR diagram as well. So generally try to figure out what these stars are like. So a star up here would have to be very luminous, so bright, but depending on how far away it is, but luminous, and cold. Generally, anything along here is called the main sequence. And up here, of course, is, as you would expect, a very hot star that's also very luminous, very powerful. Something down here is very cold, 3,000 Kelvin, that's cold for a star, cold and very dim. And down here must be very hot and yet very dim. So it sort of makes sense along here, needs a bit of explaining up here. There's sort of a patch there, a lot of stars around there. So let's think why that could be. So along here makes sense. The brighter it is, the hotter it is, right, as you would expect, for the same distance away. Up here, they're very luminous despite being cold on the surface. And if you remember Stefan Boltzmann relation, luminosity is sigma A T to the 4. We'll ignore the emissivity term there because these are stars, they're close approximations to black bodies. That's a constant, so luminosity depends on area and temperature. So generally, it's the power of 4, so that's a huge factor there. Generally, hotter stars are more luminous, but also area matters. So these stars must be giants, and indeed they are. Anything up here counts as a giant. Typically a red giant like our star will become. Anything down here, it's very hot and yet dim, so it must have a very low area, surface area. That must be a white dwarf. White as in it's white hot. You can read that, I hope. White dwarf. So, they're unusual though. So the V in our G2V stands for 5, so G25, and it just means that this is categorized as area 5. So I think it's 1A, 1B, 2, 3, 4 is sort of along here, 5, I think that's it, but we only need to know that ours is a 5, just means main sequence. So you just got to look out for that. That means it's a main sequence. So think about the evolution of a star. Let's suppose it's a star around here like our star. Where will that go? They have asked this. It will go sort of up to there and round to here, and as a white dwarf cools, it'll go down there. So an anti-clockwise path. It might be, especially for the higher levels, you might know it might do a bit of this in and out like that for a while as it fuses heavier elements, but that's not required, certainly not at standard level. Before it moves around here, it doesn't have to do that anyway. The last thing I want to cover is spectroscopic parallax. Quite confusing, unlikely to come up, but yeah, it could. So spectroscopic parallax. Parallax, you remember, is a way to find out how far away a star is. The confusing thing about spectroscopic parallax is that it's not parallax. There's lots of historical stuff. It's like parallax in that it's a way to find out how far away a star is, but it's not parallax. But it certainly is spectroscopic. So how can we use the HR diagram to find out the distance to a star? Well, finding surface temperature is easy enough from Wien's law. You find out the peak wavelength, and that's inversely proportional to the surface temperature. So peak wavelength we can get by spectroscopy. That's why it's spectroscopic parallax, gives us the surface temperature. Then you've got to work out what kind of star it is, which you can do again by spectroscopy, by its chemical composition. You can look at, say, how much hydrogen and helium it's got to find out if it's main sequence. So suppose we have a surface temperature here, we simply go up to here and across, and we find its luminosity. If you have its luminosity and its brightness, of course, you can use this equation here to find out how far away it is. You might think, well, how do we get the HR diagram in the first place if we didn't know those distances? Good point. We had to know some distances by other ways. You can't use spectroscopic parallax to build the whole HR diagram. That would be circular reasoning. So that we have to get some of them by Cepheid variables. We can know how far away some stars are by which stars are near them, if they're gravitationally bound. And of course, parallax, actual stellar parallax for the closest of stars.